In Structures Office 1.0, we have two methods for performing plastic bending analysis. One is Gazoni's method and the other is a numerical method. And we try as much as possible to provide two methods to provide some sort of cross-checks on solutions. The Cozzoni's method was presented first in May of 1943 in the Journal of Aeronautical Sciences, and it was titled Bending Strength in the Plastic Range. The idea behind the method is to replace the true bending variation curve, this, by a trapezoidal stress variation. The FO value is a fictitious stress, which is assumed to exist at the neutral axis. And you find FO by making the requirement that the internal moment of the true stress variation equals the moment of the trapezoidal stress variation. So this rectangular area, this FO value, is your plastic, and the triangular area is the elastic, and you want the moment of these two areas about the neutral axis to equal the true stress, the true internal moment of the true stress variation. Brune, in Analysis and Design of Flight Vehicle Structure, provides values of FO in figures 3.9 to 3.32, and he plots out FO values over the versus strain for aluminum, titanium, and steel materials. And then in table 3.2, he has values of FO at the yield and ultimate. So the assumptions of the method is we're computing the plastic bending moment about a principal axis, that the section is symmetric about the axis, but we'll provide workarounds for when the section is not symmetric. The material properties are the same in tension and compression, that the plane sections remain plane, that there's no distortion of the section, no ovalization, for instance, and we're not accounting for anything like local buckling. So if you would want to find out what your buckling or crippling stress is and use that as your FM value in the method to compute your ultimate moment. As for the accuracy of the method, Brune in section 3.6 provides some definition. It's accurate for rectangular sections under pure bending with moment vector parallel with the principal axis. For a doubly symmetric section under pure bending with moment vector parallel with the principal axis, the accuracy should be within 5%. But for single symmetric sections, it will vary from practically exact to definitely unconservative if your moment vector is normal to the axis of symmetry instead of parallel, normal. So the program won't allow you to do that. It won't return a result if you try to analyze it that way. And for sections subjected to combined bending and axial load, the results will vary from almost exact to conservative. And for unsymmetric bending with and without axial load, the results will vary from practically exact to conservative. To do the Cozzone plastic bending analysis, you'll have to start out by defining a material. And an excellent source of material properties is the Metallic Material Property Development and Standardization document, the MMPDS, and it will provide the Ramberg-Osgood exponent, your yield stress and tension and compression, and the ultimate stress and tension and compression, as well as Young's modulus. It does not provide the FO value, but the program will calculate that for you, so that's not a showstopper. Inside the document you will see charts such as this, where the exponents for the different grain directions in tension and compression is shown. Then sometimes you'll see it broken out so that the exponent from initial up to yield is one exponent, and then from yield to ultimate is another. If we go over to Structures Office, you'll see you go to input the material definition. You go to the Material tab, Edit Material, click on Add, you'll get this dialog box for entering the values. You'll have to input the name, the Young's modulus, and Poisson's ratio as always. Then for the plastic bending analysis, you'll have to provide yield allowables, longitudinal grain direction. 1.0 does not use longitudinal transverse for compression and yield, and the ultimate values for tension and compression. Over here is your Ramberg-Osgood equation definition, and you'll need to input these exponents from initial to yield in the longitudinal grain direction, tension, and then from yield to ultimate. If there is no difference, then you just input the value for the exponent in both of these. But both of these values have got to be defined. When it performs the analysis, it will look at the value of the stress that you're putting in. It will decide which portion of the curve to use and use the correct exponent. And so you do that for tension, and you do the same for compression. And that's it. So these two values, these two, and these. So there's 8 values you'll need to put into your material definition. Okay, so now let's go into the program and analyze the section. So here I've loaded a cross-section, a simple I-beam, and this is taken from Brune in section 3.12, and it's example 4. In there, well, before you can analyze it, you've got to define the material for the section, and you have to define what the mesh is, and it is sensitive to the mesh. So a denser mesh will give a more accurate result. And notice that I didn't align the principal axes with the x and y because it's not necessary to do that. So I'm just analyzing it off at 45 degrees. Then I went to computations, over here Cozzone method. And it tells you it analyzes symmetric sections with material values the same in tension and compression. And we'll talk about workarounds for when that is not the case later on. So this is the interface. Up here is your inputs, here is your outputs, and down here is a shear stress at the neutral axis calculation. So you want to pick your axes that we're going to compute about. We'll choose X. And then the plastic stress value, the FO value. There's 3 different options. You can compute it from the database values using the tension longitudinal values, or the compression L values, or a given value. Brune gives a value, and it's in his example, and it was 97,000 or 19,700. And then we'll give a user-defined stress level, which he used set at 35,800 psi. And then the design moment, that is the moment that he computed for a cantilever beam at the root. It had a 600-pound shear, and at the root it was 14,000 inch-pounds. So that done, click Solve, and you'll see the stresses plotted over the section, and that you'll see that they don't go to 0. You get right at the neutral axis, just slightly above the neutral axis, you're going to have a positive, that's the FO value on either side, and then it goes to including the elastic value out at the extreme fibers. So the output shows the K factor for the section. Brune rounded that off to 1.7. The fictitious elastic stress, that's the extreme fiber stress if this was elastic instead of plastic. The moment's almost exactly the design moment, but the margin of safety is very small. The shear correction factor, that's used in the VQ over IT computation. And VQ over IT assumes a triangular shape distribution of the stress, triangular going down out from the extreme fiber down. But we have a trapezoidal stress variation. So we've got a value here at the neutral axis, and then the elastic value goes up. So this shape factor is the moment of these, each element. It runs through a computation taking each element, computing the moment about the neutral axis for the trapezoidal shape, and then takes the ratio of that with the triangular shape stress variation. That ratio is 1.09, which agrees with what Brun gives. And then the first moment is the first moment of the area above the neutral axis. Down here is how to compute the shear stress, the maximum shear, which occurs at the neutral axis. And he gave a value of the thickness, which is a 1/8 inch thick section, and he gave 600 pounds. And you'll see here it says that it's computing the max shear at the neutral axis using C, which C is the shear correction factor, and then VQ over IB. And then the margin of safety is from the database, the shear ultimate in the longitudinal direction. So if we compute that, it gives a shear of 3,052. Brun shows 3,042, but there is some differences in the value of his elastic stress and the K factor. And the margin of safety is 12. Let's take another case. Let's go to computing. We're going to compute the plastic stress value from the longitudinal tension values in the database. And we'll use the ultimate for this material. It's aluminum. It has a 62,000 tension ultimate allowable, and solve it. So now you see your stress plot, and the value at the moment was 25,156. So now to check that, which you always should do, go to the plastic analysis. And we'll give this a name and 45 degrees. So the numerical method can work at any angle, and it works on composite sections, so it's a little more general. But for this case, we've got a doubly symmetric section, and so let's just go ahead and solve it. It does a bunch of checks on the balances of the stresses and tells you whether or not it passed. Down here is the moment about the neutral axis. It computed 25,235, and if we compare that with the allowable moment in the Gazoni's method, it's 25,156, almost identical, well within the 5%. So that's it for the basic doubly symmetric section analysis. For unsymmetric sections, we can compute a plastic bending moment if we walk through this procedure. You divide the section at the elastic center along the principal axis, then mirror the halves, and then since that mirrored section is symmetric, we can compute the moment, and then use 0.5, half of that calculated moment for each half, and add them. So let's just walk through that procedure. So here's the section. It was taken from Brun. Let's begin by creating a couple of subsections. And then let's move the two pieces of this section down underneath the lower half. Open that up, and then we'll copy, set the current section to the upper half, because whatever we paste in is always going to go into the current section, and we'll paste it. And then let's go do the other one and paste it. So now we have we have duplicated that original section into two subsections. Now let's compute the section properties, and we'll take the y value of the elastic center. Okay, now let's go over to, we're working on the upper half, so let's go to construction, add a rectangle. We want to keep the upper half, so we'll set the origin point to 4 and the direction point to 3. No rotation. We're going to create a negative shape here. The origin we want to be a little bit less than 0, so let's say minus 0.25. And the width of, well, the height is the value we got from the elastic center, and let's make that 3 by 3 and add it. Okay, now if we do the union of that, we have just the upper half of that section, and now we can let's duplicate that and mirror it vertically. So I click this point here, click OK. Now I have a symmetric section that's mirroring the upper half. Now let's go back to the lower half, set the current subsection, and this time we're going to chop the top off. So let's go to computations or construction, rectangle. We got a y value, v, and minus 0.25, and let's make that 3 by 3. It's a negative. Add it. Oops. Add it. Okay. Compute the union. And now let's mirror that vertically. About this point here. And okay. Now let's apply material. So here we are working with the lower half, and I've assigned a material to it. And the next step is to mesh it. It is sensitive to the mesh, so a more denser mesh is required. So I'll put 1,000 on each side. Then let's go up to Gazoni's method, and let's compute using tension L values, and use the ultimate. I won't worry about a design moment right now. So there's our moment for these. Now this is a doubly symmetric section, and we've computed a moment of 17,470. So let's record that. So the procedure is we want half of that. So here we have the moment. And times 0.5. So that's the lower half moment contribution. Now let's get rid of this. Go back up here, set it the upper half, and let's do again. Set it to 1,000 on each side. And go back over to Cozzoni's method, and again we'll use tension ultimate and solve it. And there we got 17,671. Go up to the calculator. $17,571 is our answer. So that's how you'd analyze a unsymmetric section. So now let's go back to the original cross section, which is example 4 in Brune, section C3, and see how our results compare I've created this section here, and let's go up to plastic analysis, and we'll give it unsymmetric section. Neutral axis is 0, and we'll solve it. So here is our results. We see 16,731, which is different from our, it's lower than the value that we got. So let's see how far off those numbers are. So we had 17,571 from following that procedure, breaking the sections in half and mirroring them. And then we got a difference here of 16,731. And then let's divide that by 16,731 to see how far off it is. And it's 5% off, which is what Broom predicted. It would be within 5%. So I would tend to use, this would probably be a more accurate solution, since it's a true stress plot over the section. So that concludes this section on the unsymmetric bending analysis. So now I thought we'd walk through how the value of FO is computed. If you're not interested, you're not going to lose anything by not going through this section of the presentation. So let's go over to the derivation. There's several derivations out there. The one I like the best is Tishihiro Tanabe's presentation, which you can find by Googling it. And if you recall, let's go over here, that the value of FO is a fictitious stress that is assumed to exist at the neutral axis at zero strain. And the value of FO is determined by making the requirement that the internal moment of the true stress variation, we're integrating this, is equal to the moment of the assumed trapezoidal stress variation, which is our approximation. And computing the moment of our approximation is very simple. It's just the plastic rectangular area times the distance from the neutral axis, and the triangular area times the distance from the neutral axis. Notice that he's using epsilon here as the height of our rectangle. And one of the things that Cozzone stated was that if you solve for FO over a rectangle, it's accurate for all other sections. So that's what we're doing here. So let's walk down through it. Here's the Ramberg-Osgood equation for strain. Here's our moment, this part here. It's the rectangular area moment, the triangular area moment. And then what we want to solve for is that equals the integration from the neutral axis up to epsilon, which we're setting equal to the strain, the real value of strain. So it looks a little strange that it looks like a virtual work expression. It's got nothing to do with that. This is simply the stress times your d epsilon, which is a rectangular area part of this curve here, times the epsilon, which is your moment arm. Then he takes the derivative of epsilon with respect to stress, and he gets the d epsilon as a function of df. Then he multiplies this equation by stress, And then he plugs it into, so now we have our f d epsilon, and we have our epsilon value. Here's epsilon, and here is your f d epsilon, here. So now he's integrating up the integrand to integrate from 0 up to the maximum strain is now been converted to integrating up to the max stress. And then he just carries through the integration process. So here's our true strain moment about the neutral axis, this expression here. And then he sets the two equal. This is the trapezoidal moment. This is the true moment, internal moment. And he solves for FO. And that's this expression. And then down at the bottom here, he takes some materials from Brune, and he gets the FO ultimate and yield from the test data that Brune gives us. And he calculates these values, add ultimate and yield, and compares them. So that wraps up the presentation. Please contact us if you have any questions, and let me know how it's going. Thanks for listening.